Hi there, we've got exercise 8a here. We're going to look at Maclaurin expansions. This is Colin Maclaurin, sounds a decent chap, name like that. You can just tell by the picture it's a fair time ago, and the fact that we're still doing it indicates it's quite useful maths, so I'll crack on with it. First of all, I'm going to start with binomial expansions, which are actually an example of a Maclaurin expansion, a very particular type of a Maclaurin expansion. So if you remember when we did this, we had this formula which was I'd called the 1 plus nx formula in normal maths, and 1 plus nx plus what is it? It's n minus 1 over 2 factorial, etc., times by x squared plus, and it goes on forever. So all we had to do in each of these examples was state what n was, so minus 3 over 2, and also say that, well, in this case x is really minus x. So I can chuck those in. It's 1 plus, there's my n, times by my x, plus n minus 1, you just knock off 1, so it's minus 5 over 2 over 2 factorial, and then minus x squared, and then the last one, minus 3 over 2 minus 5 over 2 minus 7 over 2 over 3 factorial, which is 6, minus x cubed. So if I work this out, I get 1 plus 3 over 2x, that one's easy to do. This is 15 over 8, and it becomes a positive. I think there's actually four negative signs there. So 15 over 8x squared. This one's a bit trickier. So 15 times 7 on the top. Divided by 8, divided by the 6. I get 35 over 16. And I reckon it is a plus, because it's minus, 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 minus. So it's 35 over 16x cubed. And this one is, notice that all 1 plus ones, these are relatively nice ones. N equals minus 3. The x becomes 2x. I'm going to leave you to do that one. And also I want you to do this one where the n is a half and the x becomes x squared. So I want you to try to do these two. I'm going to put the answers up so you can then check your answers, and we'll see how you get on. So there's the answers. So hopefully you got those right. If not, go back and have a look at binomial expansions in normal maths. The Maclaurin series, look, this is an odd formula. This is certainly a bizarre formula, but it tends to make more sense when you do an example. We're going to see this a lot. Now basically it says you can write a function as a Maclaurin series expansion if you know what the function is at 0 and what the f dash, notice that's the differentiated version of the function at 0, and the double differentiated version of the function at 0, and you actually do this number of times, or as many times as you want. Usually they say you have to do it for 3 terms or 4 terms or something. So we are going to have to differentiate our function and keep differentiating our function and keep subbing 0 into the answer. And notice you then times it by either x or x squared over 2 factorial, or x to the, well, x cubed over 3 factorial, x to the 4 over 4 factorial. So I want to use this example. It says f of x equals sine x, and that's my function. And I want to find a Maclaurin expansion for it. Now I'm going to have to differentiate it, or you can't do this unless you do the differentiations. And when you're doing the differentiations, just get my pen back, I think it's gone. When you do the differentiations, you just need to make note of how many times you've done it. So just be clear that when you differentiate f of x, f dash of x equals cos, you should remember that. You've got that sign, then cos, then minus sign, then minus cos when you differentiate these things. So f dash equals cos, f double dash, well, is minus sign. It just switches between the two. And then eventually f triple dash, I suppose, is minus cos. And if you do it another time, you go back to the sign and just repeat. So I've actually written all those down. And it says that because it says if we want to find the first 5 terms, bizarrely I'm going to need, because look at this, you see, yeah, I think some of these will disappear, and I'll show you why in a bit. So if I substitute 0 into this first one, f of 0. Now if I put 0 into sine of 0 is actually 0. So that kind of disappears. That's why I'm thinking I'm going to need more than 5 terms. In fact, I think I'll need 10 terms because every other term is a 0. And if I do f dash of 0, f dash of 0, well, that's cos. Now cos of 0, you put 0 into cos, you get 1. So effectively, when I put all these in, it's going to go from 0 to 1 to 0 to minus 1 to 0 to 1 to 0 to minus 1. Now I'll keep doing it. It's a weird example, but it's a good example. And then if I put those numbers into here, well, I'll get f of x equals, well, f of 0 is 0, so I might ignore that, plus x times by f dash of 0, that was 1, so that's just an x. Plus the next one I can ignore, it's this one, sorry, and this one I can't ignore, so this is the one with a 3, we'll say x cubed, so that will be x cubed, but I've got to times it, or divide it, sorry, by 3 factorial, and I've also got to times it by the minus 1. So when you do all this lots and lots of times, you end up, I reckon, with, there's my x for the first one, there's my minus x cubed over 3 factorial, the next one will be plus x to the 5 over 5, and you keep doing this, and I've got there 1, 2, 3, 5 terms. There you go, I have got 5 terms. So you might think, well, that's a bit weird. Why would I do that? Well, again, there are times when algebraically playing around with sin x is quite tricky. So instead we prefer them in the same way that we do with binomial expansions. We prefer them if they're polynomial expressions. And of course, these are only valid within certain bounds of accuracy. This one that we just found, just missing the bit of the formula at the top. If I drew the sin x graph, that's my original graph. And if I want to compare that to this expression that I've just done, this x minus x cubed over 3, etc., this is it. Now, on the first glance, they're almost identical. In actual fact, they're not almost identical. This is an x to 9 curve, so at some point it stops kind of repeating itself. And already you see here, that's quite close to there, but then it carries on going, and here it doesn't, it turns again. Everything else up to, it looks like between 4 and minus 4, looks really accurate. And this, of course, is when we've done up to the x to the 9 type. We could have gone up even longer and further. And in actual fact, if you do it for all terms, an infinite number of terms, I suppose, it's more than just that. It will actually be true, it's accurate for infinity. X belongs to all real numbers. So this formula, this Maclaurin series, as we call it, is actually quite accurate within the bounds of accuracy stated for each one. So the OCR formula book gives us a number of these formulae, and so you'll notice it gives me this one here. This is the one we're going to use today, but it gives me a lot more. And I just did sine. There's the one I just did. In actual fact, you can be asked to use it, or you can be asked to prove it. That's the one we just proved. It's got a horrible end bit here, but you can more or less ignore that. It's the first bits you care about. So let's have a look at this. It says, find the Maclaurin series of log of 1 plus x. So I suppose what I need to do, if I'm going to do this, I need to first of all know what, well, let's write f of x equals the log of 1 plus x. And I need to differentiate that. So what is f dash of x? And you should recall that if you integrate 1 over x, you get log x. So by definition, we should recall that if you differentiate log x, you get 1 over x. So this will be 1 over 1 plus x. And then you have to times by the differential of 1 plus x, which is 1. So in actual fact, that's it. So now what's f double dash of x? That means I go to this and I differentiate this. Well, this is actually, I suppose, better written for now as 1 plus x to the minus 1. So using the chain rule again, it's minus 1 to the front, 1 plus x, knock a power off, times by the differential of that, which is still that. and then f. How much he wants up to the fourth one, so I need to do 3 more. Third differential is move the 2 to the front, which gives me 2 lots of 1 plus x to the minus 3. And then f, the fourth differential, you can see why after a while you get bored of writing like that, of x. And I reckon that is minus 6, 1 plus x to the minus 4. And what I have to do now is I have to chuck naught into all of these things. So f of naught is the log of 1 plus naught. Log of 1 plus naught is really the log of 1, which is 0. So that will disappear. F dash of 0, if I put 0 into this, it's 1 over 1 plus x. So that's 1 over 1, which is 1. F double dash of 0, well, this really is minus 1 over 1 plus x squared. And the great thing about 1 plus x in all of these is 1 plus 0 will still be 1, so you can almost ignore it. This will give me minus 1. F triple dash of 0. Well, what's this? This is 2 lots of that. So that's 2 lots and it's positive. I reckon that's 2. And F 4 dashes of 0, I reckon is minus 6. So therefore, chucking it into my formula, f of x becomes, f of naught disappears, f dash naught times x, which was just 1, so that's just x. X squared, it just goes off, x squared over 2 factorial. So it's this answer for this, so it's minus 1 over 2 x squared. The next one will be a plus, and it will be x cubed over 3 factorial. So I'll have an x cubed, it'll be over 3 factorial, which is 6, but it says 2. So I suppose that can be better written as a third. Is that up to x to the 4? That's right. So plus, well, it says minus 6 over 4 factorial is 24, x to the 4, and of course this is better written as a quarter. So the answer is x minus a half x squared plus x cubed over 3. And me, I've been very lazy, I've just put out the proper formula. But you can see the next one is x to the 4 over 4. And actually, this is a standard formula. This is a formula we're meant to know and use and be able to remember that we, it's in the formula book, but we're meant to know that it's there. So what I want you to do is just to have a play with this. You will be doing a lot of differentiation. You'll be doing a lot of substituting zeros into those differentiations and then putting those answers back into this formula. And this is probably your best example of how to do it. Notice what we did. We differentiated every one. We sub 0 into every one. We got our numbers. We sub this into the formula. So best of luck. Exercise 8A, page 173.